All right, guys, welcome. This is Business Calculus 12.5. We're talking about absolute maximums and absolute minimums. We've learned so far how to find maxes and mins by a sign chart, and they're all based on the first derivative. So today we're finding absolute maximums and minimums. Okay. So for an absolute max and min, it is, to be an absolute maximum, it is the absolute highest point of the graph, right? It's the highest point of the graph. Okay, so if you look at the chart down below the graph, so here, this would be the representation of an absolute maximum. This point at 0, 4 would be the highest point on the graph, and it is the only high point on the graph. So that's what being an absolute maximum is. If you're an absolute minimum, you are absolutely the lowest point on the graph, and that can be represented by the third graph. Here, 0, 0 is the lowest point on the graph, therefore it's the absolute minimum. Okay, and then let's say that, look at the first graph. You see that this tail heads towards infinity, that tail heads towards negative infinity. This means there is no absolute high point and there is no absolute low point. Therefore, this point here is just a local maximum, and this point here is just a local minimum. Not an absolute max, not an absolute minimum. So today we only want to focus on finding absolute maximums and absolute minimums. All right, so that's what we want to look for. All right, so down below, for extreme value theorem, what this theorem says is that in order to have an absolute maximum or minimum, the function must be continuous on some closed interval a, b. So for these four graphs, what we have done is close the interval. So in the very first graph, we close the interval from 2 to 12. This means we close the graph. It's still continuous, and the reason we say it's continuous is because there's no breaks or holes in the graph, and all the points are defined. So here we close the interval 2 to 12. This means since we close the interval, f of 12 is the absolute maximum, f of 2 is the absolute minimum. Okay. And this is only because we have closed the interval. The second graph, we change the interval from 4 to 10. Now, our maximum and minimum change. My absolute max is now at 105. My absolute min is now at 73. And this only happens when you change the interval. And then, on the third one, we change the interval again from 4 to 8. My absolute maximum stays the same at 105, but now my absolute minimum changes to 78. And then the very last one, we change the interval to 3 and 11, and now I have an absolute maximum. I have two absolute maximums. Both are at 105. So here and here are considered two absolute maximums. Yes, we can have multiple maximums, absolute maximums and multiple absolute minimums. Okay, and down here, I have the two absolute minimums, both at 73. Hey, it's a smiley face. Yay. Okay. Okay, so that's all our extreme value theorem is saying, is that in order to have an absolute maximum or minimum, we must have a closed interval. All right. And look at this lovely theorem. I will be referencing this on the next problems. It says absolute maxes and minimums occur at critical numbers or at endpoints. Remember, critical numbers come from the first derivative, and endpoints come from our interval, which is going to be given in the form of AB. Cool? Cool. All right. Number one, finding absolute extrema. Find the absolute extrema of the function x cubed plus 3x squared minus 9x minus 7 on each of the following intervals: -6 to 4, -4 to 2, -2 to 2. Okay, step A, check to make certain that f is continuous over the interval AB, over the closed interval AB. Well, this is going to be the easiest points for you because, again, since you're in business cal, you're only going to get polynomial functions. So the domain of all polynomial functions is always all real numbers. So there's your domain. Okay. Then find the critical numbers in the interval AB. So you know how to find critical numbers. Take the first derivative, set it equal to 0, solve for x. That's it. So that's what we're going to do for the above. So f prime of x is equal to 3x squared plus 6x minus 9. And then set it equal to 0. We get 3x squared plus 6x minus 9 equal to 0. And solve for x. First thing I can do is get rid of the 3. I'll say divide 3, divide 3, divide 3, divide 3. The reason I do that is because it's the greatest common factor. I can divide everything by 3. This then becomes x squared plus 2x minus 3 equal to 0. Factor it. I should get x plus 3, x minus 1 equal to 0, and x equals -3, and x equals 1. These are my critical numbers. Okay. Now, evaluate the original function at the endpoints A and B and at the critical numbers found in step B. Okay. So I'm going to put my intervals here. So the first interval we want to use, I'm going to write it right above it, is -6, 4. The second interval we're going to use, -4, 2. And the third interval is -2, 2. Okay. Now, just like it says, we only want to evaluate the endpoints and the critical numbers. That's when I said I was going to reference this little theorem here. The only reason we want to use endpoints and critical numbers is because those are the only places that absolute extrema will exist. That's it. We don't have to choose any numbers other than the ones we're given and the critical numbers we just found. So let's try it out. So my critical numbers are -3 and 1. There we go, there we go, there we go. Okay, cool. So I'll put in my endpoints, -6 and 4. And then the biggest question here is, do my critical numbers of -3 and 1 fit in the interval -6 and 4? And that question is yes, or that answer is yes. So I'll put them in here, -3 and 1. If you want to put them in order, you can, in case if it's all jumbled out of order, you can put them in order. Doesn't matter though, as long as it's just the endpoints and the critical numbers. And make sure your critical numbers fit in that interval. which ours do. -3 and 1 fit in this interval, -6 and 4. Okay. There we go. Okay, so now what we're going to do with these numbers is just what the directions say above it. Plug into f of x. You are going to plug these in to the original function. Plug these in to the original function. X cubed plus 3x squared minus 9x minus 7. Okay. And I plug them in, -6 gives me -61. 4 gives me 69. -3 gives me 20. And 1 gives me -12. And all we want to do is look for the absolute maximum and the absolute minimum. So look at your y values. What is the smallest y value? That happens to be -61. So this means that we are going to have at this point, it's too much of a color. Let me see. There we go. And -6 and 61. This will be our absolute minimum. Okay. And then look for the largest y value. The largest y value happens to be at 4 and 69. That will be my absolute max. That's it. That's all we're looking for. Nothing else. Let's do it again. I'll put my endpoints in, -4 and 2. And then I'll put in my critical numbers. But I have to make sure, do my critical numbers of -3 and 1 fit in this interval? -3 definitely fits, and 1 fits. And again, take these numbers and plug them into the original function. If I plug in -4, I get 13. If I plug in 2, I get -5. If I plug in -3, I get 20. If I plug in 1, I get -12. Again, let's look at the y values. What is the smallest y value and what is the largest y value? Those will give me my absolute maximums and minimums. So my smallest y value is -12. So at 1 and -12, that will be my absolute minimum. And then look for the largest y value. That happens at -3 and 20. So that's my absolute max. Perfect. Okay. Then the very last one, -2 and 2, I'll put my endpoints. -2, 2. And then I'll put in my critical numbers. Does -3 fit in this interval? No. So we leave it out. Does 1 fit in this interval? Yes. We'll only include the 1. Since -3 doesn't fit in the interval, we do not include it, which makes our calculations a little faster. Once again, plug these into the original function. -2, I get 15. 2, we get -5. 1, we get -12. Again, let's look for those absolute maxes and mins. And the smallest y value is at 1 and -12. So that is my absolute min. -2 and 15, that is my absolute max. And that's all we're looking for. That's it. So take the derivative, find your critical numbers, see if your critical numbers fit in the given interval, and plug all the numbers into the original function. This will help you look for maximums and minimums. All right, and that's it. The absolute max of function f on the interval AB is the largest value found in C. The absolute minimum of the function on the interval AB is the smallest value found in C. And when I say C, I mean step C. That's it. It's everything we've done already. Okay. Let's do it again. Find the absolute extrema of x to the fourth minus 8x squared plus 16 on the following intervals. So like I said, step A, easy money. What's the domain of this function? You're only going to get polynomial functions in this class. So your domain is always -infinity to infinity. Okay. And then B, find the critical numbers. Take the derivative, set it equal to 0, solve for x. That's it. Here's my function right there. There we go. So ugly, stop it. So it's not obeying me. Obey. F prime of x is 4x cubed minus 16. Minus 16x. 4x cubed minus 16x. Okay. Then take your derivative, set it equal to 0. 4x cubed minus 16x equal to 0. And then solve for x. Take a 4x out. That should leave me with x squared minus 4 equal to 0. Factor again, 4x times 4x times x minus 2 times x plus 2 equal to 0. Now, set all three of these terms equal to 0. I get 4x equals 0, x minus 2 equals 0, x plus 2 equals 0. Here, divide by 4, x equals 0, x equals 2, x equals -2. These are all my what? Critical numbers. That's right. Critical numbers. Okay. Now we have our critical numbers. Now we want to test them in the intervals. So I'm going to write my intervals here. -1 to 3, 0 to 2, -3 to 4. Before moving on, I'm going to punch this function in my calculator. X to the 4th minus 8x squared plus 16. Okay. Okay, now there's our charts. We're going to start with the first interval, -1 and 3. I'll put my endpoints, -1 and 3. And now we ask, do our critical numbers fit in this interval? Does 0 fit? Yes. Does 2 fit? Yes. Does -2 fit? No. So that's where we stop. Okay, now plug these in. -1 gives me 9. 3 gives me 25. 0 gives me 16. And 2 gives me 0. Once again, look for the absolute maxes and mins. So 2, 0 has the smallest y value. That's my absolute min. 3 and 25. That's my absolute max. Okay, next one, 0 and 2. There's my endpoints. Now look at my critical numbers. Well, it just so happens that 2 of my critical numbers are 0 and 2, and -2, again, does not fit. So, again, calculate 0. 0 should give me 16. 2 should give me 0. Look at that. Absolute max. Absolute min. Last one, -3 and 4. Does 0 fit in there? Yes. Does 2 fit in there? Yes. Does -2 fit in there? Yes. We have them all. So let me go back. -3 gives me 25. 4 gives me 144. 0 gives me 16. 2 gives me 0. And -2 gives me 0. Okay. Now look for the smallest values, and looks like 0 is the smallest y value. So both of these are going to be my absolute minimums. That's my absolute mins. And then the largest y value is 144. So 144 is my absolute max. All right, there it is. That's simple. That's all we're doing. Okay. Okay, so what we have up next is something called the second derivative test. So remember when we were graphing using the second derivative characteristics for concavity, we had to find the second derivative, set it equal to 0, solve for x, all that good stuff, right? Well, what the second derivative test does is helps us locate maximums and minimums without creating a sign chart at all, which means you wouldn't have to create a sign chart for, what is it? The first derivative. Okay, so with that being said, if let C be a critical number of f such that the first derivative at C is 0, if the second derivative at our critical number is positive, then the original function at that critical number has a local minimum. 2, if the second derivative at that critical number is negative, then the original function at that critical number has a local maximum. Now, the second derivative test is to make our life easier, so we don't have to make a sign chart for the first derivative. You can choose to use it or not. And one of the reasons you can say not to use it, because if the second derivative test fails, you still got to make a sign chart. So use it or don't, up to you. Okay, so let me fill out this chart. So for the very first one, it says the first derivative at the critical number is 0, and the second derivative at that critical number is positive. This means that the original function will be concave up, which means at that critical number, we'll have a local minimum. And what that means is that if you have a local minimum, your graph should look like this. You'll have a local minimum. Okay, for the next one. The first derivative at your critical number is 0. The second derivative at your critical number is negative. This means that the original function will be concave down, which means the original function at that critical number will have a local maximum, which means your graph will look like this. Now, third line. First derivative at the critical number is 0. Second derivative at our critical number is 0. 0 tells us nothing because 0 is not positive and 0 is not negative, which means the test fails. And if the test fails, then you have to make a sign chart, no matter what. So that's why I say use it or don't, up to you. But I think in these examples, we want to use it. So example 3, find the local maximum and minimum for each function. Use the second derivative test for local extrema when it applies. Okay, so find the critical numbers, plug them into the second derivative to see where local max or min exists. So we're going to try to use the second derivative test here. So the very first step is find the critical numbers, okay? So that's what we're going to have. We got all the room in the world too. Okay. So let's say step A, find the critical numbers. And to do that, that means we take the first derivative, which gives me 3x squared minus 12x plus 9. We set it equal to 0. And I get 3x squared minus 12x plus 9 equal to 0. Divide everything by 3 because that's the greatest common factor. And we have x squared minus 4x plus 3 equal to 0. Factor that. X minus 1, x minus 3 equal to 0. Solve for x. X equals 1. X equals 3. These are my criticals. Okay, I need to check something really fast. Oh, I wrote too big. Maybe I can fit this here. Okay. So B, step B is use the second derivative test. So this means find the second derivative. So we want f double prime of x. So what was my first derivative? Oops. My first derivative was 3x squared minus 12x. So my second derivative is going to be 6x minus 12. Okay. Now, what we want to do, if we're using the second derivative test, is take these critical numbers, and plug them in for x. So this means that we'll get f double prime of 1 and f double prime of 3. Plug those in to the second derivative. You're taking your critical numbers, you're plugging them into the second derivative, and I'll tell you what the output means. Hopefully we don't get a 0. Oof. So you get 6 times 1 minus 12, that gives me negative 6. And then 6 times 3 minus 12, we get 6. Okay. So what this means is that by the second derivative test, look at the very first one. F double prime equals negative 6. What this means is that by the first derivative test, the second derivative is negative, which means that our graph will be concave downward, which means at our critical number of 1, we will have a local maximum. That's all that says. So what we can say here is that since by the second derivative test, since the second derivative is negative, this means that x equals 1 is a maximum. Which means, I bet you can guess what is going to happen for the next one. But I'll go over it with you anyways. Let's look at it again. And now look at, I need that sign chart up there. There we go. Now look at it. At f double prime of 3, we get a positive 6. This means that at the critical number, the second derivative is positive, which means the original function will be concave upward, which means at our critical number of 3, we'll have a local minimum. So what this means now is that x equals 3 is a minimum. Okay. And now you remember how to find the exact location. So if we wanted to find the exact location of these max and mins, we would plug these values into the original function. Plug into f of x. And that would give you the exact location of the max and min. We don't have to do that now. I just wanted to show you how the second derivative test works. Because did we have to make a sign chart at all to find a maximum or minimum? No. But if you like making sign charts, then you don't have to worry about the second derivative test at all. Just keep going. Find your critical numbers, make a sign chart, pick test points, find where it increases and decreases, and that'll help you find your max and min. Okay, that's it for that one. All right. Example 4, same exact thing. Find the local maximum or minimum, use the second derivative test when it applies. So again, let's go ahead and find critical numbers first. That's our first step. I promise not to write so big this time, I hope. A. Find critical numbers. So that means f prime of x is going to be x to the 5th minus 20x to the 4th plus 100x cubed. And then set it equal to 0. And factor out an x cubed. You get x squared minus 20x plus 100. And then factor some more. And set these equal to 0. You get x equals 0 and x equals 10. I'm only going to write 10 one time because it shows up twice, right? So that's it. These are the crits, right? Critical numbers. Hey, we still have room. Perfect. Okay. B, now find the second derivative. B, we're going to use the second derivative test. So f double prime of x is 5x to the 4th minus 80x cubed plus 300x. 5x to the 4th minus 80x cubed plus 300x squared. Okay, and now once again, you will take these values, these critical numbers, and plug them in for x. And let's see what we find by the second derivative test. Okay. So you'll have f double prime of 0 and f double prime of 10. I can tell you now that if I plug 0 into my second derivative, that 0, that 0, that 0, which means we get 0, which 0 tells us nothing. So this means that the second derivative test fails. And if it fails, guess what that means? We have to make a sign chart. Okay, but that doesn't mean 10 is out of it yet, just yet, right? That doesn't mean 10's out just yet. So I'm going to take 10 and plug it into my second derivative. If I plug in 10, oh, nice. 10, we also get 0. So, fail, fail. 5x to the fourth minus 80x cubed plus 300x squared. Yep. So this means we create a sign chart. So fail, fail, or a bunch of failures. We now move to step C. We create the sign chart for f prime of x, since we failed. Okay, so with that being said, sign chart. Plot our critical numbers, 0 and 10. My intervals, -infinity to 0, 0 to 10, 10 to infinity. Numbers, 3 intervals, 3x values. From -infinity to 0, -1. From 0 to 10, 1. From 10 to infinity, 11. And we are plugging these in to the first derivative. Which means let me go back up to find my first derivative. X to the fifth minus 20x to the fourth plus 100 x cubed. Okay, come down here. -1 gives me -121. 1 gives me 81, and 11 gives me 1331. Okay. So negative, positive, positive. So looking at this, we are negative, positive, positive. This means we decrease, increase, increase. So if we're looking for max and mins, will we look for a sign change? So the first number to look at is 0. 0, we decrease and then we increase, which means 0 will be a local minimum. So I'll say x equals 0 is a min. And then next one we look at is 10. And at 10, you increase and increase. So x equals 10 is nothing to us, since there was no sign change. So x equals 10 is neither. Okay, and now if you wanted to find the exact location of your minimum, right? You would take x equals 0 and plug it into the original function. And that one's probably not bad. If we plug that into the original function, which is up here, if you plugged in 0, all of that would become 0. That means our local min's at 0, 0. Huh. So I could say that. There it is. That is absolute maximums and minimums and the second derivative test. Once again, you don't have to use the second derivative test because, like the very last example, the second derivative test failed, which means we still have to make a sign chart for the first derivative. So use it or don't, up to you. That is it.